For today's mini lesson on capacitors, I've taken a page out of Mrs. Getz's book and giving this little tutorial a shot. That way when we have any online office hours, I don't have to teach as much. I can just answer questions. So I want to do a quick Chapter 30B Capacitors lesson. And I put a bunch of videos online, obviously, but it never hurts to have another way to listen to things. So firstly, capacitors. These are all capacitors right here. And the best way to think of them as they're sort of like temporary batteries. They just store charge. And just like a battery doesn't really generate charge, but it pushes charges through. So you have one end is positive, one end is negative, and so there's two key things here. This one right here, this formula, is a lot like the resistor formula. Remember this whole formula was like R rho L over A or whatever. That doesn't like, once you have, remember we had like our little color-coded resistors. You have color-coded, not color-coded, sorry. You have capacitors that have different capacitances. And changing the voltage didn't change the resistance of a resistor. Like, it's a 10 ohm resistor, that doesn't change. So like, you can't like, oh, let's have more voltage and that'll make the capacitance go up or something like that. Or that's not how it works, right? Just like V equals IR was a thing. You have your resistor, 10 ohms, 20 ohms, 30 ohms, whatever. You have a certain capacitance, right? And what are the things a capacitor depends on? And so a capacitor is going to look a lot like a battery, with its symbol is going to be, let's see if I can draw it here. Oh boy, that is not good. There we go. It's just two solid lines, one of which is positive, one of which is negative, and you can even see it on here. You might have a positive and negative. And the actual, like, how does it actually work? This is what, like, a capacitor has two parallel plates, and we've done this before, so there's like an E field between these guys, right? We've done parallel plates before, but it's actually called a capacitor. One end is positive. Why? It's attached to a positive part of a battery, so the charges kind of start moving around. Like, you think like, oh wait, there's a space. Why would the charges move? Well, if the space is thin enough and you start pushing positive charges out here, out of this guy, they start moving this way, and little positive charges on this plate start moving. Oh, so you actually do have a current that flows. It's weird. How can you have a current with an open space? But if it's small enough, there is influence across that space, right? And in that formula, which we had before, which was right here, this D is going to be the distance between the plates. A is the area. So it kind of makes sense. Like, the bigger the area, so if I can get my different color here, right? If you have your two plates, so let's say I have like a large plate that looks like something is going on here. So you have these two large plates, and this is supposed to be three-dimensional. So a bunch of positive charges on this guy and a bunch of negative charges on this guy. So there's a distance between them. If you make it narrow, if you make this distance smaller, the capacitance goes up because you're able to like affect the charges on the other side, right? So even though one side's negative, it had equal negative and positive beforehand. Like a capacitor that's uncharged does not have a positive and negative. You've got to attach it to a battery. And so let's get like some of this out of here. Let's go. So the area, more area, you would be able to store more charge. That kind of makes sense. The capacitance. Epsilon 0 is a constant, kind of like the resistivity. And then K is called the dielectric. So you can put some garbage in here to make it even more effective. And that's what that little K is. So this right here, this capacitance of a capacitor right here, these guys, does not change. When you apply more voltage, if I put 1.5 volts or I put 3 volts, so here we have a 1.5 volt battery. If I put 3 volts here, does not change the capacitance of this thing. What will it change? Oh, could it change the charge when you attach a battery? But the actual capacitance, which is measured in farads, like Faraday, right? So you could figure this out. Just like resistance was in ohms, we have another guy who named stuff after himself, farads, right? Microfarads. The bigger that is, the more stuff you can store. So that should sort of make sense. So anytime they ask you about surface area, right? So this is like the actual capacitor. How much charge is when you attach to a battery? So just like a resistor has some ohms, doesn't matter what's attached to it, it has a resistance. V equals IR. So if I just said, oh, back when we did V equals IR, we had a certain resistance. You hook it up to a higher voltage, you get more current. Well, the same is true here, except the formula is that the voltage is going to be charge per capacitance, or it's going to be C equals, I've seen it written like this way more. I don't know why AP writes like this. Charge per voltage, right? If you change this around. How many charges per volt can you store on this thing? And that's going to be the idea. The big, oh, this guy's a big boy. I can't read it, but it's like 4,700 microfarads or whatever. These are little tiny guys. If we had been in class, we would have played with these. So let's go over some answers, right? So I'm not going to go through and spend all time. You can go ahead and pause the video if you want to try this yourself using those formulas. But basically, the first one uses your capacitance formula, and the second one uses this sort of like a V equals IR thing, where you have to know that the charge per volts, more volts, you get more charge, right? Because it kind of makes sense. If I make this 3 volts all of a sudden, boom, I have more electrons being pushed over here. I'll store twice as much charge. Oh, and also the Q on this plate, when they say what's the charge on one plate, that is what this formula finds. Because they are the same charges. If this is, if like this turns out to be what, 1.5 times 10 to the minus 6 positive charge, whoa, and this would be 1.5 times 10 to the minus 6 negative charge. So they're going to say which charge is on the plates. They just mean one of the plates because the other one is just the other sign. Other formula that you should know, go back to this, just the energy stored in something. It's actually derived in number 5 in the problem set if you really love calculus. But basically it kind of makes sense. How much energy is stored, just like how much energy is in a battery. It relates to the power, the charge voltage, or you can kind of use either of these formulas for how much energy is stored. So that kind of goes over number 2 type of question where it says like how much energy is stored in the capacitor. Let's get a different color here. And then average power. Oh, right. So far I've talked about analogies of like V equals IR, right? And we've talked about resistance is equal to rho L over A, but now we also have P equals I times V. Remember this guy, right? Back with resistors. The current times the voltage. Well, there's power that's dissipated in a capacitor when it's discharged. Ooh, talk about that later. But basically, you charge it up. Kind of makes sense. As you charge this capacitor, you're going to push positive charges on it, Eventually, it's going to have way too many positive charges. So what is going to happen to that is that, let's get rid of this stuff, boom, boom, boom. Eventually, it will also get to that point. Now, it doesn't instantaneously do that, but this will also be 1.5 volts. Because, and then what you do is you go, boop, all right, let's take this battery off. You now have a mini 1.5 volt battery. It doesn't provide 1.5 volts, but it starts at 1.5 volts. If now I took this and attached it to, let's say, a resistor of some sort, which we'll do later, then all of a sudden, like, whoa, it's like a battery, current flows. Of course, it runs out of juice. Unlike a battery, is 1.5 volts for a very long time, right? Eventually, it will run enough chemicals, but the capacitor just discharges. That's what that means. So you charge it up and it discharges. So the most it will get to is 1.5 volts, but as it discharges, that voltage drops. So that's what makes like those more difficult questions. In the packet, number 4, given a parallel plate capacitor, derive the equation for capacitance. This is a kind of a cool one that if you think about like Gauss's law, right? Ooh, Gauss's law. I thought it was so useless. It just had to do a sphere as well. If you think about like something that's has a plate, you're just going to have a rectangle around it. So it's actually the charge is going to be just the electric field times the A. Now A is just the area of this rectangle, right? So if we have this rectangle here, sort of the idea, whoa, that's terrible. Um, so the charge, you can kind of go ahead and derive. Basically, this is the formula that you're given. So like, where the heck did that come from? It comes from Gauss's law, and we put in this thing called a dielectric, which we'll talk about in a second. So if you want to see where it came from, that formula, you can kind of look. It does come from Gauss's law. Oh, no, we're going to dielectric. Forgot that part. So dielectric. It wasn't in this problem. It's in number 3, maybe? What is the point? The point is, let's go back to this one. Perfect. A dielectric is if you put some garbage in here, right? Put some garbage in there. That will kind of not allow, because what you don't want is the positive charges to jump across this space, right? You're trying to store them. So how would you store them? Well, you actually have like a little material in there. You can have a little plastic. You can even do water. Not that you would do that in a computer, but that would kind of prevent. It would allow more charge to build up here. So when you see that formula of what is K, if they don't tell you, it's 1. If they tell you, oh, a dielectric's put in there, which is 2, that would actually make the capacitance bigger. You could store more charge on that. So just so you know what that K is, that wasn't in this question. And last but not least, for capacitors, they're sort of weird. They are completely the opposite formula of resistors. And if you think about it, the capacitors in series are 1 over, right? So you actually lower the overall capacitance, whereas if it is a parallel circuit, you're going to add the capacitances. And I think this makes a little bit more sense, right? So if you look at number 8, you have your parallel capacitances. Think about like you're pushing charges off here. So charges can either go to this guy or they can go to this guy, right? So that they basically have 2 places where they can store. That's supposed to be a positive. They can have 2 places where you can store charge. So it kind of makes sense that capacitors in series add up to give you a bigger capacitor. I think that one makes a lot of sense. Like, whoops, sorry. So if you look at that formula in parallel, you add up all the capacitors. In series, you do the 1 over rule because this voltage is divided amongst the 2 things. So where you had charges on this one, now they're going to put positive charges over here. And basically, you've divided your voltage amongst the 2 things. So each of them has less voltage, so each of them has less charge. So overall, it makes the capacitance less, is the idea. So you might remember resistors, right? So if you remember resistors in series, they had the same what? They had the same when they had like this. So here's your battery. Oh gosh, I'm still working on getting used to this slate. Resistors in series, it was you add up the resistances. So, I mean, currents were the same, voltages divide, right? But if you look at this, so now with capacitors in series, what's the same? Not current, but the charge. Any charge that's on this guy has to be on this guy also, right? Because the electrons are getting pushed off of one. I should say the positive charges are getting pushed off of one. And so they're going like around, there we go. Are they really going around? No, but they're pushing, right? So they get to this point like, stop here. And then these guys, these positive charges push over to here, making this negative, right? Leaving this guy positive. Then the positive charges on the other side here go, whoa, 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 let's get out of here. Let's go back to the battery. So just like currents are the same, here your charges are the same. And what you should get is that, So let's see. Okay. Next one. Let's see. I'm just looking at my notes here. Why did I just do V1? All right. Anyhow. Yes. Oh, good, good, good. Yes. Okay. So this should have been, sorry. So that's why I was like, why do I have 6 written there? These should both be 3. I'm crazy. Voltages divide, right? So if you think about overall, you have less capacitance. So you're going to have a certain amount of charge. The total voltage over the equivalent capacitance gives you the overall charge. That charge is true for both of them. So you should get that 6 volts is the overall voltage, right? Because that's the overall. I shouldn't have put V1. This should be V total right there. Sorry about that. And then your equivalent capacitance is 4. Your total charge is 24, and your total voltage is 6 volts. So that just sort of makes sense. Next but not next and last for this little tutorial is this one where you've added up, so you get your overall capacitance to be more. So each of them are 8, so your total capacitance is 16. You're able to hold more charge. So 6 volts with 16 microfarads gives you 96 is your overall charge, but your charge is divided between the two. Oh, this is like, remember currents dividing was with resistors. That's still true. Instead of current, you have charge. So in parallel, charge does divide, and your voltage is the same. So that sort of rule is the same, right? So like you get 6 volts, they're in parallel, they both get 6 volts. They split the charges, okay? And just to back up again, let's go with, where are we? There we go. So this one again. So I had it written wrong. Sorry about that. So overall, 6 volts. Remember in series, your voltage divides 3 and 3, but your currents are the same, or in this case, your charges. So they have the opposite rules. Similar ideas, but opposite rules for the overall capacitance. But the voltage doesn't change. The voltage is still divided when it's in series, and it's still the same as in parallel. The charge is divided in parallel, but it's the same in series. It's just the formula for the equivalent capacitance is what's different. So hopefully that helped a little bit. Let me get rid of this right here, and let's see if I can stop this. I don't know how to do this. I'm going to get there. All right. Well, I think that should be good, and hopefully if you have any questions, you can email me or visit office hours.